Hi, to finish up chapter 9, we're going to go with section 9.7, where we're going to take a look at some of the most important formulas that we have for combinatorics. The Pascal formula, the binomial theorem, and the Pascal triangle. So first, the Pascal formula, it just says that if you have positive integers n and r, with r being less than n, then choosing r out of n plus 1 is equivalent to just choosing r minus 1 out of n plus choosing r out of n. The reason why this is true, and we can do this combinatorial proof by separating n plus 1 in two sets. Either x of n plus 1 is going to be included in the first one, or is not. So if it's included, then we can choose the remaining r minus 1 items from n items. So we're going to get the first part. We're going to get choosing r minus 1 out of n. And then plus, if it's not included, then we choose r out of n items. So we'll be choosing r out of n ways. Notice that this is the way of counting where we have two disjoint sets, and so we're checking what is the amount of options that we have in each of those disjoint sets. So that's why this general choosing out of n plus 1 becomes and choosing r minus 1 out of n in case the x n plus 1 element is included, and in case it's not, then it's choosing r out of just n. One example of this application formula in practice would be, well, I can think about the choosing 3 out of 6 as choosing 2 out of 5 and 3 out of 5 and adding those. The thing about that is that notice that we're pretty much basing the result for n plus 1 in terms of the result in n. So that's going to be fundamental because that's the basis of what we call the Pascal triangle. So in the Pascal triangle, we have ones being built along the sides of the triangle, and then each entry below is equals the sum of the two entries directly above it. So for example, you see here we have line of ones, but then below the 1 and 1, you get the 2. Below the 1 and 2, you get the 3. Similar, the 2 and 1, you get the 3. The 1 and 3, you get the 4. The 3 and 1, you get the 4. The 3 and 3, you get the 6. So on and so forth. The 1 and 4, you get the 5. 6 and 4, you get 10. 6 and 4, you get 10. 1 and 4, you get 5. And you can continue doing this for all the integers, for all the lines and rows of the triangle that you want. Now the idea is that this is going to give you the row n position r from the left starting from 0 is going to be equals then n combined r. So for example, this is row 0, row 1, row 2, row 3, row 4, row 5. And so we're going to get next the row 6, which will be the combination of the previous elements. So for example, we're going to go to row 6, entry 2. So row 6 position 2, then we can have that as phi combined 1 plus phi combined 2, which is 10 with 5, which is going to be 15. So you're going to have 15 here. You're going to have 1, 6, 15, and then you're going to have here for the entry 3, you're going to have 20, which matches with this row 6 position 3. And of course, we're talking about in terms of what will be not counting the 1. We're not counting the 1 because we start in position 0, position 1, 2, so on and so forth. So this will be position 0, position 1, position 2, position 3, position 4, so on. Okay, so why is this is also useful for the binomial theorem? So the binomial theorem is for any real number a, b that are non-negative and any integer n, the binomial a plus b power to the n can be seen as the sum from k equals 0 to n of n choose k, and this is what's coming, giving me the coefficient for the polynomial of a power to the n minus k times b to the k. So one example of this would be a plus b power to the 4. So notice that a plus b power to the 4 is 4 choose 0, a to the 4, 4 choose 1, a to the 3 times b, 4 choose 2, 4 choose 3, 4 choose 4. Notice that the exponent, the start to go down. So this start k equals 0. So initially is a to the n, b to the 0. So b is not there. So because n is 4 in this case, then we get a to the 4 first. Then you start reducing. K equals 1. You're going to get a to the 3b, a to the 2b to the 2, a b to the 3. And finally, it's going to end up with when k is equals 4, then we're going to get b to the 4, and a is going to disappear. And of course, the combinations are going to give me the coefficients from the polynomial. So because of this, you get the coefficients are 1, 4, 6, 4, 1 in the row 4 of the Pascal triangle. This is very useful because then I can find coefficients of particular powers for specific polynomials without necessarily having to do the full expansion like I'm doing here. So when expanding a plus b power to the n, we're really multiplying factors of ab together. And each term in the expansion comes from choosing either ia or b from each factor. And the term a to the n minus k times b to the k, we're choosing b from exactly k of the n factors. The number of ways to choose that is, of course, n choose k. Some useful cases here that we're going to have for some proofs in the future is if you have that a and b are equal 1, well, we're just going to have this identity here where the list sum from k equals 0 to n of n combined k is going to be 2 to the n, which is the total of number of subsets of an n element set. So this is the power set, and this is the proof of why the powers of a particular set has cardinality 2 to the n when the set has cardinality n. And if you have a equals 1, b equals minus 1, well, of course, that's going to be 0. And that just gives me the identity that minus 1 to the k and choose k is going to be 0, which can be useful for proving things with series. All right, so in summary, we just learned the Pascal formula here. We learned how the Pascal formula works for the Pascal triangles and arranges all the possible choosings of R out of n. And each entry is the sum of the two above. And then the role that this is going to have in the binomial theorem. We have some special identities that we learn. And so we're going to be doing much more exercises of this on the class notes. So make sure that you don't miss those because we still need to go over plenty of problems once that we have defined all these different formulas in the binomial theorem. Some common mistakes that you want to avoid is that you don't want to be applying the Pascal formula with the wrong indices. So you want to make sure that the terms are correct, both on the right and the left. So note that both terms on the right use row n instead of not n plus 1. So here's n plus 1, but here is n. For the binomial coefficient in a plus b power to the n, each of the terms in the binomial coefficient is n choose k, a to the n minus k, b to the k, not just a to power n minus k times b to the k. You also got to be careful with the exponent on the binomial expansion, especially on the exercises where we're going to be comparing powers. And sometimes the powers are a little bit more disguised or they have more terms that are not immediately evident, so you got to be careful with the exponents. All right, this is the end of chapter 9.